I'm Eric Bohm. I'm the Senior Research Programmer with the Parallel Programming Laboratory at the CS Department. The goals of the Parallel Programming Laboratory are to do what we call application-oriented computer science research, particularly with a focus on supercomputing and parallel computing, also both large and small, so down to the single multi-core desktop all the way up to the very largest computers that exist. And our feeling is that the best and most useful research for everyone is when we can build tools that other people can use for their research, not just to satisfy our own curiosity about computer science goals. Our primary tool is the Charm++ runtime system, which is our scheme for facilitating parallelization. And it provides what we call an object-oriented solution for parallel programming. And with this, we've collaborated with a number of groups to produce applications for different science goals, such as the NAMD application for molecular dynamics, the Changa application for cosmological research and simulation, and the OpenAtom application for quantum simulation of material science, and a number of other applications, one of the newest ones being a collaboration for the simulation of contagious disease. The paper that we're presenting at this Supercomputing Conference 2011 is discussing essentially the lessons that we learned while evolving the NAMD application to support both extremely large systems and to run on extremely large machines. And to do that, we had to address essentially a number of challenges with respect to distributing the data and loading all the data, because it was a much larger amount than most NAMD users typically want to do, and also scaling out onto 224,000 cores of the Cray XE5 machine Jaguar. The first challenge that we really had to come to grips with was just loading systems of this size. The original scheme that had been used in NAMD for 10 years was essentially just a single processor scheme to grab a single file, load it up, and then distribute the data. If a system is 100 million atoms, it won't actually fit in the memory of a single node. And so we had to explore different ways of dealing with that, and we found essentially two main approaches. One is to actually parallelize the reading process so that we actually distribute the readers across hundreds of cores. And additionally, we also found that there's a tremendous amount of redundant information in the system itself in its normal expression. Essentially, every single atom will have its coordinates, and it will also have the type information about the atom, hydrogen, oxygen, etc. But most of these systems are composed of a huge amount of hydrogen and a huge amount of oxygen and a huge amount of carbon. And so if we decided we could just use the atom signatures, the type, and compress that away and keep only the unique data, the coordinate information, as that which is being distributed everywhere. And then with the type information, we can simply do a lookup for the type. This allowed us to get both a data compression in the footprint that we were actually storing on the entire machine, and also to actually distribute both the footprint of the data and the time required to load the data. An additional approach that we took for this case is that we're following the trend of these large machines increasing the number of cores per node. And so, and the amount of memory per core is not generally increasing very much, and depending on how you want to look at the trend, in some cases it's actually decreasing. And so we needed to be even more careful about how we were using memory on a node and how we were distributing the computation within a node. And so we developed what we call the shared memory version of CHARM, or SMP, sort of the little acronym that we've been using to describe it. But essentially the idea is that we make a single process for the node, and we make essentially one compute thread for every core minus one, with the final compute core being dedicated to communication. So this allowed us to make sure that the compute operations were nicely predictable and that they weren't being interfered with by communication from exterior nodes or taking the burden of communicating to exterior nodes. Instead, the communication thread would absorb all that in one place, which would allow us to very finely tune how the communication thread worked, and separately, as a separate region of concern, optimize how the computation worked. And so this allowed us to have our load balancers work across nicely predictable behaviors when we're measuring how much time it takes to compute, so we could redistribute the work very efficiently, as opposed to the non-SMP version of CHARM, where every core would be doing both computation and communication. And every time a communication event occurred, it's essentially asynchronous, and you can't predict when it's going to happen and what kind of perturbation it's going to cause in your measurement of the computation. And so this scheme gave us both a nice division of labor and a separation of concerns, and the ability to actually speed everything up by distributing things very carefully. The other addition of doing this with the shared memory in a single process is that information that would normally have to be replicated across the processors within a node and increase the memory footprint is now shared, so it only exists one time per node. One of our goals is that we would be able to work with more scientists and computer scientists in the evolution of these ideas that we have with respect to the ways to do parallel computing. And our particular approach is one where we prefer to have the very careful separation of concerns between what the application programmer is choosing to do in terms of decomposing their problem in logical units for the problem that they're trying to solve, and delegating maintenance tasks and various kinds of balancing and system tasks to the runtime system, so that they don't have to take care of all these individual things in addition to doing their science in their application.